Yeah, and so we started recording, and so the question was about power laws which emerge. Okay, then just maybe we go. Although I said that it's not too useful to just repeat the lecture recordings, but as long as there are no specific questions, I think it's still one possibility. So let us go ask once again. If anyone has something very specific to ask, which would be helpful, let us say Kaspar and Kristlin have already said something, and see, Raido, do you have anything which you would like specific to discuss? Or how was the recording, lecture recordings more or less clear and understandable?
Well, maybe this is a bit general, but still. So why does the energy go like to these peak scales? Like what stops it from going to the or dissipating? So yeah, the inverse cascade, basically, I did not understand it still very well.
Okay. All right. So let us then start discussion, and so what we have in 1D. Sorry, 3D case, we have energy conservation law, because as long as we ignore dissipation, viscosity puts 0, then we have Navier-Stokes in that case would result in total energy, which is a kinetic energy, as conserved. So in that case, we would have integral v square d. Today it's see why it's writing so bad. So v square integral v square d cube r integral over volume is conserved, is constant, and then what is different in 2D, we discussed it already, but in that case we have another conservation law. Actually, we have many conservation law, and we can see even infinite number of conservation laws. But in what we are using here in particular is that omega vorticity squared d cube r is constant, and this is called entropy. And so we have one more conservation law, and that's what makes different 2D and 3D. And now this brings us to what we discussed last time, which is the spectral cascade. So let us start with 3D. 3D, and in 3D, what we have is that we discussed it like before, because we have vorticity flux is conserved. What happens with vortices? We have a vortex, which means that we take here material loop, and then consider the field of vorticity. So we have omega, which is defined as omega is vector. Omega is curl of velocity field, and then we have a vorticity flux. Certain goes through it, and then what is conserved is the flux of vorticity, which means that omega dA over this material loop is constant. And then what happens in fluid is that material lines become stretched. And so if we took initially, if we take here a material cylinder, which is built on vortex field lines. So here is certain initial cylinder, which is made so that our vorticity lines will not cross it. So everything which is inside remains inside. So at the surface, we have also vorticity field lines lie on the surface of this cylinder. And now as time goes on, what happens with the cylinder, we know it from the mixing of passive scalars already, that this cylinder becomes stretched. So it becomes something like that, very long, very narrow, surface area goes also down. Something like that. It's what it evolves into. So cross-sectional area will be reduced. So here is this cross-sectional area of this tube will reduce. And now we can see that vortex, we can call this was initial vortex, which we have left, and now it is stretched. Now it is narrower. So if it was previously described by certain characteristic scale A, now it is described by some A prime, which is much smaller than actually at the end of the day, it's much smaller than A, but for time being, let us write it smaller than A. So we can see that here is a certain cascade is happening from large scale to small scale. So vorticity here is transferred from large scale to small scale. But because the flux is conserved, so we see that actually vorticity itself is not conserved. So we have roughly speaking, omega times A is constant, A times L is a volume, this is also constant. So A is inversely proportional to the length of material line, but omega vorticity is inversely proportional to A due to the first relationship. And then because A is inversely proportional to L, and then omega is proportional to L. So actually omega grows during stretching, mixing. And so omega itself now is not conserved. So we don't have any conservation of an entropy like we have in 2D case. But then again, we can certain velocity speed, we can associate it. And we can say that we had big vortex before, and now we have narrow vortex. So energy of the vortex, big vortex became now energy of a small vortex. And here we can still say that this energy now is transferred from big vortex to small vortex. And now we just need to calculate what is the energy transfer rate through spectrum. So if we consider certain characteristic time, ask what is a characteristic time tau associated with scale A? Tau as a function of A. Then in order to make, let us say, the vortex 2 times narrower, we need a characteristic time tau, which is on the order of hydrodynamic rotation time. So let us say how long it will take for a water particle here and water parcel here and water parcel here to depart to a distance which is 2 times bigger. So here is A, here is 2A. So how long it will take? And this is estimated as a characteristic speed associated with scale A. So if we have vortex of size A and it moves with speed V relative to the center of the vortex, or just the relative speed of 2 parcels at distance A, then we can say that, now I write better colon here. So we have certain characteristic speed which is associated to the same scale, and we can estimate tau as just the kinematic time it takes to make a full rotation, or just to move to distance A. So distance divided by speed is the time. This is estimated as distance divided by speed. Okay, and now we have expression for a characteristic time scale tau expressed in terms of velocity. Okay. And then we ask next, what is a spectral transfer rate? How much energy is transferred per unit time to vortices which are smaller than A. So we see that energy is transferred from big vortices to small, and spectral energy flux, energy per volume. This is like energy which we denote joules divided by cubic meter, for instance, and divided by seconds. Per unit volume and per unit time through spectrum. And then those vortices which had size A now become A divided by 2, roughly speaking, during this characteristic time tau. So we take energy of those vortices and divide it by characteristic time. So this is energy divided by characteristic time, how long it takes to make them 2 times smaller. And energy itself is energy, but this is energy density, like energy per volume. And this is just the velocity square multiplied by density 1/2 also, if you like. And then this also already takes care per volume because we have density rho. So it is mass v square, mass times v square would be the energy, but we divide by volume, so it becomes rho. Rho v square divided by 2 would be estimate for energy. We can neglect actually that 1/2. This is not significant. We want to have scaling, so numerical factors we can ignore, and divided by scale tau. And now we plug in tau from the previous expression, and then we obtain that this would be v cubed divided by A and multiplied by rho, which is constant. And this is the energy flux, how much energy goes per unit time through to vortices which are smaller than A. And because we assume constant spectrum in time, so this must be constant. And this means that from here we can immediately obtain how needs the speed associated with scale A, scale with A. So because v cubed divided by A is constant, then we can say that v, now why doesn't it write v, must scale as A to the power of 1/3 cubic root of A. All right, so this tells us that characteristic speed associated with vortices of certain size A go down as a cubic root of the scale A. Now, is this part more or less clear, or there are some things which I need to explain in more details? How you feel?
What was A exactly? I couldn't catch on. The small A.
Small a is characteristic size of a vortex. So I consider vortices which have characteristic size A. Yeah, okay, you can think about it also in this in such terms that let us say we have initial velocity field, and which has in full details, and then we can make it so that we average over like a sliding window of size A. So maybe I take next page. So we have initially a full detailed, like streamlined behave very convoluted way, but then I take a window of size A and average over this window. And once I average, then this field line, like the convoluted parts smoothes away, and now it becomes, let me make it different color. So here now, after smoothing, it becomes something like that. And then the whole curve becomes after once I average over the window size A, then this is the resulting picture. And now this is what after such an averaging, I average out the small scale fluctuations of velocity field, and that's what remains. And I can say that okay, this is these structures here. So each of them can be considered like a kind of a vortex or velocity field fluctuations on that scale. Oh well, another way to approach it. So we have a velocity field as a function of coordinate, v as a function of r. And then I make here Fourier transform, and then I obtain v as a function of k, as a wave vector. V as a wave vector. And then I make here coarse graining, meaning that I so if I have certain Fourier components, Vk as a function of k as a function of x. Okay, and here I basically need to have real part of it and imaginary part. Okay, let us consider one of them, and then we do the same with imaginary part. Sorry, it's not x but k. As a Vk as a function of k. And this is certain as a fluctuating function. And then I take a certain k naught here, and then certain k naught and 2 k naught. And then I apply here windows that say that I cut off everything else which is outside of that range. So after applying this window, what remains is a curve like that. Here it fluctuates like the original, but outside is 0. So that I can express that v as a function of k as sum over different coarse graining parts. So this is over k naught equals from the smallest scale, k smallest, to k largest. No, how should I write it? So that k not each k next. Maybe a little differently. Let us make it so that kn equals k naught multiplied by 2 to the power of n. So each we have some smallest k naught, and each next k in is 2 times bigger than the previous one. And this goes to up to the certain maximal value k max, what we have over there. So I divide the whole spectrum P of k into different different segments. Let me redraw this same graph again. So here is the real part of Vk. Here is axis k, and then I have certain smallest k naught here. Then we have 2 times bigger is my k1, 2 k naught. Then I have here k2, which is 4 k naught. And then I have k3, which is 8 k naught, and so on. So I split the whole v as a function of k into functions which each of them is non-zero only in the given window. So first coarse graining component is here. Next coarse graining component is here, and then next one is here. So, but separately, each of them contains only certain range of k's. But if I sum them together, then I have the whole Vk which there is. So this is like a coarse graining of the velocity field. So let me complete now what I was writing. So here has a V as a sub Kn. So this is a coarse-grained velocity field, V sub Kn. And then I can take reverse transform that a V at scale wave vector and characteristic scale are related like a reciprocal to each other, where velocity which is V sub A, V sub An. N's characteristic scale, where An is 1 divided by Kn, which is the largest scale A max divided by 2 to the power of n. Each next one is 2 times smaller than previous. If wave vector goes growing, the characteristic scale goes decreasing. So each of them is inverse Fourier transform. So this is now integral V Kn e to the power of I kx dk. Something like that. X is a vector with 3D vector now. And now I'm not sure if this was helpful, but actually, since you asked what is the characteristic, what is a vortex, or what is that V sub A? V as a function of A. So V as sub A is velocity, coarse-grained velocity field, which includes only fluctuations which have correspond to characteristic scale A. Now, Kaspar, was it helpful or it was the other way around confusing?
Well, it's not Kaspar who asked, it was me, but
yes, okay, see, sorry.
It got a lot more confusing, so I.
All right, but let us try because this is important. Let us try to get it clear what we are speaking about. So, suppose you have image. Have you ever played with photos with certain in Photoshop or in somewhere?
I don't have Photoshop.
Okay, but then you can image that you have a photo. Okay, now how to explain it? If you don't have a photo, haven't played with Photoshop. If you have Photoshop, then I would explain such a way that you take a photo and then you play with the same image J. Actually, you can also play exactly what I discussed here. We can you could do also with the image J. All right. Just I'm trying to figure out how to explain it the clearest way what we are doing. Let us make another attempt without Fourier transform. Without Fourier transform. Now. Now, what happened? Why I cannot? No. Maybe if I can take here on screen, play with some photos, maybe it could be helpful. Okay, let me try doing it by hand. So we have here certain. Let us consider one-dimensional example. What do I mean? So one-dimensional example is that suppose we have certain Brownian function. Let us say Brownian function. here is a coordinate of Brownian particle, and here is a function of time. We discussed it, how it looks. So it goes like that. We have small scale fluctuations here. We have small scale fluctuations. No, it's not writing. And then we have large scale strengths here. It goes something like that. Okay. And now this is x as a function of this is x as a function of t. Okay, now my touchpad touch screen went crazy again. X is a function of t. And now this we represent as a sum of a coarse-grained components. X sub a, where each next a is 2 times bigger than the previous one. We divide over all the a's. And now what is x sub a? X sub a, each of them is a function which has only fluctuations corresponding to this scale a. So let us say that here is this here is unity. Okay. Unity, and then x sub 1, which corresponds to scale 1, would be function which would fluctuate only at scale 1. So unlike the previous one, now it has only fluctuations which with single characteristic scale. It can go up or down, but it can also stay here below. But the main thing is that it cannot have big trends like going very far away, and it can have cannot have smaller scale structures than this one over here. So this is now this is how x sub 1 behaves. It can something like randomly fluctuates, but the scale at which it changes, characteristic scale at which it changes, is 1. Now we can take again this is x sub 1 as a function of t. Now let us take x sub 2. X sub 2 is something which fluctuates only at the scale of 2. So x sub 2 is now the blue one, which goes something like that. Okay, this is x sub 2. Now x sub 4 would be in green, and this is something which fluctuates only at scale 4. 1, 2, 3, 4, something like that. All right, and then if we sum them all together, then the sum of all these things is the original one. So if we sum everything like that, we have obtained this convoluted curve, but each of them separately has only one characteristic scale. See, is this like more helpful now?
Well, yeah, it's kind of like what Fourier transform, I guess, is.
Yes,
like
exactly.
meant
That's why I was starting explaining in terms of how you can do it in terms of Fourier transform. But in order to understand what it is, you don't need to have a Fourier transform. Just we decompose initial convoluted function with fine structures into some of simpler functions, which each of them has only one characteristic scale. So the convoluted function x of t is a sum of coarse-grained components. These are coarse-grained components. Coarse-grained. All right. Siim, how are you? More or less okay?
Yeah, I understand the steps, but still I don't have like an intuitive sense of what like A is. Like I cannot like see it in my head. It's like
Okay.
I understand the steps.
Yeah,
but
A is very simple is the thing. It is the scale what you have. Like if you take a teacup, and move with spoon over there, then you have vortex which has characteristic size corresponding to the size of your teacup. So there you have only until it moves all regularly in vertical way, then you have only one coarse grain component present basically, which the scale A corresponds to the radius of the cup. But if you have turbulent motion in there, if you just shake it and make it like randomly moving, then you may have, or let us say you have take a pot and then let a stream of water flowing into it from tap. Then the water moves in the pot in a complicated way, and then you have turbulent motion in the pot, and then you have many scales present. You have big scale, small scale, smallest scales, and then, but you don't have, there is still that so-called Kolmogorov microscale, and you won't have anything which is smaller than the Kolmogorov microscale, because everything dissipates out there. If you had small vortices over there, they would just dissipate, lose energy before the energy is transferred to them. So yeah, intuitively characteristic scale, that's exactly what, so if you want to speak about turbulence in intuitive way, it's exactly in terms of the characteristic scale, or everything else is very mathematical. But if we speak about in terms of characteristic scale, that's the only way to have it like more intuitively. Are you still in trouble with it?
I'm just trying to make sense of it. So like basically if I have some sort of like a random turbulent vortex, and if I want to describe the characteristic size of it, then I can like use the Fourier transform to see what describes like, I don't know, like what sort of power law describes the size of vortexes basically. Or I'm like trying to word it out exactly like in like one sentence.
Fourier transform is if you want to do things mathematically, which might not be helpful if you want to develop intuition. So just Fourier transform is just to have also a mathematical rigorous way of dealing with it. Which Fourier transform, we can mathematically separate all those scales: scale 1, scale 2, scale 4, scale 8, and so on. We can separate them all strictly and nicely. So okay, it's like maybe you can also think in terms of maps. If you take a world map, then let us how you see Estonia over there is a small, very small thing, which is basically in the best case you can still resolve Estonia, but you won't have like if you look at coastline, it's just only one small loop maybe. Let me make another page here. In world map, if you take at the largest full world map, Estonia would be something like maybe that. And then if you zoom in, just look at magnifying glass, it would be something like that. But then if you take a little better resolution map, then what you see is here maybe we have here maybe more details. You can see at least islands, okay, Saaremaa here, maybe also Hiiumaa, here something like that. Maybe also Muhu and Vormsi in the best case, but maybe Vormsi already is too small. So now you have a more resolution. So here we have only one characteristic scale present corresponding to around 100 kilometers. But now we have characteristic scale which are present correspond to something like maybe 30 kilometers here present. So now we have a different coarse graining. Here our coarse graining has also scales present which are 30 kilometers. So how can we go even more intuitive than that? I don't see any kind of possibility. Coarse graining means like separating different scales. And yeah. What about the rest of you? Are you okay? Or are you still also confused? Kasper, how do you feel?
I mean, I more or less understand it, I think.
Kristlin?
I think the map example cleared it up a bit, but if we go back to the next, to the last page.
Yep.
Then in our example there, where we have these three different x1, x2, and x4, in there, could we say that the x1's characteristic scale is 1 because it only takes the one length, then x2's characteristic scale is 2, and x4's characteristic scale is x4?
Yes, exactly. That's it.
Okay. Yes, then it's understandable.
Yeah. Raido, you are okay?
Yeah, I'm okay.
And coming back to Steam now, are you slowly starting getting better here, or?
I mean, a bit, but still, I'm not confident at all at this.
All right, and then yeah, if we now look once again what we did here before, then I say that what happens with the vortices as time evolves. As time evolves, because vortices become stretched, and for one, we can all look at how the material volumes move. So everything which had vortex which had certain characteristics scale A has now 2 times smaller characteristics scale A. Well, it becomes bigger, but that's not the point, because if we look at certain intersection, what we see, like it matters how far do we need to move to see something else. So as long as we move from the center of the vortex to distance A, then we have something new. It was before, but now after it has been stretched, we don't need to move already to distance A, but we can just remove to distance A divided by 2. And we have outside of the our material tube. The material tube is over here. Now, yeah, material tube is over here. Now it became like that. We needed to go to distance A to get out, but now we need to go to distance A divided by 2 to get out. So that's why you say that now characteristic scale became 2 times smaller. But energy comprised in it is still conserved because of energy conservation law. And now we can say, because of that, we can say that energy which was associated with scale A is now associated with energy at scale A divided by 2. So we had a spectral flux of energy. And spectral energy flux, which is energy transferred per unit time from vortices which are bigger than A to vortices which are smaller than A, is estimated as the energy density of those vortices at scale A divided by time which needs for them to transfer from size A to A divided by 2. So time needed to transfer from size A to A divided by 2 is just the hydrodynamic rotation time of a vortex, the size of a vortex divided by the speed. And if we plug in, we obtain that energy transfer, energy flux, spectral energy flux is velocity cubed divided by A. And now what we discussed last time, our condition for a stationary spectrum is that energy flux must be constant, spectral energy flux independent of scale. So this guy here should not depend on scale A, which happens only if V associated with A is proportional to A divided by 1, A to the cubic root of A, so that V cube cancels out with A. And this is what we call direct energy cascade. Now, Raido, is this transfer energy cascade now more or less clear?
Yeah, this part was quite clear, I think.
Yeah. And so what happens with energy now is that it's transferred from larger scales to smaller scales. So if we plot here energy as a function of scale A, then here scale A, so it transferred from large scale to small scales. And okay, if v square v went as a to the power of 1/3, then v square goes to a to the power of 2/3. And so these energies velocity squared. So this is an increasing function power law of A. It goes something like that. And energy is transferred from large scale to small scales. And then this power law is valid. But if you take a log plot, then it becomes straight line. Any power law in log graph becomes straight line. ln e sub a, and here ln a, and then it becomes a straight line. And then energy is transferred from big scales to small scales. And this is valid until dissipation starts playing a role. And once dissipation starts playing a role, everything dissipates. It goes away. So now we have two scales. This is energy input scale, the scale at which we make the medium moving. Like if we speak, for instance, in terms of atmosphere, then this is a scale where sun heats that goes into motion, for instance, or if you have like a volume of water, like behind a ship, for instance, or something moving in water, then it is the size of the body which moves, the size at which you input energy into the volume. And then this evolves to smaller scale, and here is dissipation scale. Dissipation, and you can in the Kolmogorov turbulence, this is called the smallest scale here is called Kolmogorov scale, Kolmogorov microscale, microscale, and the range from the input scale to the Kolmogorov microscale. This is called inertial range. Inertial range. So these are like important concepts which is helpful if you know and understand what they are. So we have input scale, dissipation scale, or Kolmogorov microscale, and then we have an inertial range between the input scale and dissipation scale. So in the inertial range, you have power law. So power laws are valid within the inertial range. All right. And then perhaps it's time to move to inverse cascade. But before going to inverse cascade, do you? It's still opportunity to ask about this. If anything is still confusing or not clear.
So the dissipation point or the dissipation range, that is out of inertial range, right?
Dissipation point, the Kolmogorov microscale, it's the end point, the limit of inertial range, where inertial range ends.
Okay.
From initial to input scale, this is the inertial range. Here I draw it in terms of A, but you quite often draw it in terms of a power spectrum and wave vector. In that case, you have here just a logarithm of P, ln of P of K, and here you have a wave vector K. And then this other way around, you have a small k corresponds to big A. So it's like a flipped figure. So we have here this microscale is at the right-hand side. Here we have dissipation range at left-hand side. Now it's at right-hand side. Now we have things like that. And then pk corresponds to k to -5/3. I think this was also in the lecture recordings. So just this A to 2/3 corresponds to K to -5 over 3. This is if you work with Fourier spectrum and compute their power spectrum. Here is now input is here, input, and here is dissipation. And inertial range is between those two. And energy goes from input scale to the dissipation scale. Transferred from big vortices to small vortices. Now, before going to inverse cascade, any questions?
I maybe have a bit of a stupid question, or maybe I didn't just quite understand, but the dependence that V depends on characteristic scale A times 1/3, that is only applies when our energy is conserved, right? So, but
Yeah, but well, not exactly. It is valid in the case of a direct cascade of Kolmogorov turbulence. So when velocity scales as a scale to the power of 1/3, this is valid in the case of direct cascade, which happens in 3-dimensional turbulence. And energy is conserved. Energy is conserved if we are above dissipation range. Energy is conserved. The only thing what okay, let me write. Maybe that's useful. Yeah, what I need to have the direct cascade. Let me write it. Typing in is better probably. So power law. V is proportional to A to the power of 1/3 or pk drop to k to the power of -5/3 is valid when when first we have 3D, which means no entropy conservation. Entropy conservation. Two, scale energy is conserved, which means we must be above the Kolmogorov microscale. So it is to neglect dissipation. Dissipation and 3 scales must be smaller. Than the input scale, because if you had some energy input at those scales, so if you input energy, then also energy is not conserved. We cannot have energy input at those scales. So this energy must be the spectral transferred and not coming from outside at those scales. So usually there is like a big gap between the input scale and the Kolmogorov microscale. If we speak about, for instance, atmosphere, in the atmosphere, Kolmogorov microscale is around a millimeter, about millimeter scale. which means that above that there is no input. What air moves just freely by itself. That you won't be moving, putting more air in motion at centimeter scale or meter scale. It's at much bigger scales where you put air into motion. So you have no energy input between, like if you input maybe if you input input energy. Okay, what can input energy is let us say some buildings. If you can speak about turbulence about certain buildings, then you have the size of a building, maybe something like 10 meters. 10 meters, 10 meter scale. Then you have from then initial range is from 1 millimeter to 10 meters, which is quite a lot. But if energy, if you input energy like 1 kilometer scale. Like some heating of some fields, for instance, then it's even bigger. Then even bigger. But if input at or like 100 kilometer scale, 1000 kilometer scale, like sun is shining at over 1000 kilometer range, then it is not the case, because then atmosphere becomes two-dimensional, atmosphere 2D, and then we arrive at the Innes cascade actually. All right. Krislin, is it more or less clear now?
Yes, it's clearer now.
Okay. And now, shall we move to Innes cascade? So in case of Innes cascade, 2D and Innes cascade. Then we have two conservation laws. And then we have entropy cascade. And it works the same way. So what is conserved now is vorticity, which is omega square. But this is nabla of V, nabla cross V squared. And now if we make the same type of estimates, then V associated with scale A, we just nabla cross V, nabla is taking derivative is dividing by the scale. So this becomes V divided by A, and it goes to square. So omega itself is a modulus is estimated by characteristic speed divided by characteristic scale, because it is taking derivative. And if we take it to square, everything becomes to square. And now, in the same way as we did with energy, so flux now, the entropy flux is entropy, which is V divided by A squared, and the same way as before, divided by characteristic scale. But as before, the characteristic scale tau is estimated as scale divided by speed. And so everything now becomes just V divided by A. And this must be also constant. So now we obtain that now V must be proportional to A. If we have the entropy cascade, then V must be scale as scale A. And now we have two scaling laws. One is V divided by A, one is V proportional to A, and the other, but we also need to have V proportional to A to the power of 1/3. And they cannot take place simultaneously, clearly. These are incompatible. One is proportional to A, and the other is A to the power 1/3. And so the question is, what happens then? How can we have two different scaling laws? Both need to be valid. or from entropy conservation, velocity must go to as proportional to scale, and from energy conservation, velocity must go to scale to the power of 1/3. And the resolution is that yes, the both takes case, but we have different directions now because we have entropy cascade, so we no longer can have energy cascade towards a smaller scale. So we have now, if we make the same figure here, B as a function of scale A, and then we have a input scale here. And then we have, on the one hand, we have entropy cascade, which takes place towards the smaller scales. And then we have energy cascade, which goes to the larger scales. So here energy goes towards larger scale and entropy goes to smaller scale. So here we have velocity is proportional to the scale to the power of 1/3. And here we have a velocity proportional to a scale A. And that's actually which is causing all those cyclones and anticyclones. So you know that you have big scale atmospheric structures, cyclones and anticyclones. This is how it comes to existence is exactly that if you input at certain scale, but energy goes to larger scales because it cannot go to smaller scales due to entropy conservation. And so a small vortices, small in the atmosphere, sum up, making cyclones, large scale cyclones and anticyclones, which have characteristic scale is already now on the order of like the radius of Earth itself, around thousands kilometers maybe, and yeah, basically that's it. That's the main point of it. That's the main point of it. That now this is called inverse cascade. Now this is because it goes to different direction. And this once again, this happens in 2D because in 2D you have also entropy conservation. We discussed it before, right? How and why entropy is conserved in 2D. Now, how do you feel it? I think Raido needs to go soon, probably. So how do you feel, Raido? Is it more or less clear?
Today I don't have to go.
You don't have to. Very good.
Yeah.
So how you feel about it?
Yeah, I think it became clearer now.
Mm-hmm. And I think this is like out of the whole course what we had, this is one of the main points actually. It's very useful once you understand the difference between direct cascade, inverse cascade, and Kolmogorov scaling, anticipation scales, and things like that. What about the rest of you? Kaspar?
I don't know. Yeah, I don't really know. Like right now, sure, I understand maybe some of it, but cannot really like really understand it. I'm not sure.
Krislin?
Yeah, I think same.
Siim, how are you?
Yeah, it's more or less, I think. But can you go one slide back? I couldn't
Yes,
get
sure.
the additions. Yeah, thank you.
And then what is left to do is like that intermittency stuff again. That okay, this is yeah, well, of course you can do a lot of maths, and there are like interesting things if you are into maths. There is a so-called Kolmogorov 4/5 law and all those things. These are all nice, but these are not the main point. Main point is these scalings what you have here. But what is still useful to keep in mind are those structure functions about which now I am already a little bit confused. How much did we do it with the basic scalars? Probably not much. We mentioned about intermittency, right? So do you remember what was intermittency?
I only remember that we like mentioned it.
So basically, let us see. Let us see. We had that Kolmogorov 5/3 law. Kolmogorov Kolmogorov 5/3 law. Pk is proportional to k minus 5/3. Then Kolmogorov 4/5, I think, yeah. This is basically the same thing, but it states something like v cubed is equal to something like 4/5 epsilon and a, where a is like we have two particles, two fluid particles at distance a. And now you take a relative speed of two particles. VA here is relative speed. And then you take your cubed and average, and then Kolmogorov 4/5 law states something like that. So what is the difference? In a kind, it's the same thing, because we learned before that V is proportional to a to the power of 1/3. But so that V cubed is proportional to a. V cubed is proportional to a. That's what we have from Kolmogorov 5/3 law. But now what is the difference here in Kolmogorov 4/5 law is that we have not only proportionality but also the prefactor. Epsilon is the dissipation rate. How much energy is dissipated per volume? Dissipation rate. Energy is dissipated per volume. Per volume. And unit time and time. Kolmogorov 4/5 laws gives you the prefactor. But now, what is intermittency? Intermittency, if you did not have intermittency, then you would say that I can take from here anything. We can say that v to the power of n, I would expect to be proportional to v to the power of n divided by 3, right? I can take 1/3 into power of n, and I obtain, sorry, not v, but a to the power of n over 3. It would be if not intermittency. If no intermittency. So Kolmogorov later, something Kolmogorov 60 something, I don't remember, actually it was 62 or what it was. Kolmogorov himself realized that actually his previous theories are like simplifications, and in reality, the result is not so straightforward. If we take b to the power of n, and then you have a result proportional to something which in itself depends on n. So you have, this is called a structure function. And this is structure function scaling exponent. Function scaling exponent. So it is now knows that psi of n is non-linear function of n. Psi of n, non-linear function of n. And this is what is because of intermittency. Now, once again, what is intermittency? Intermittency is if system is not described by Gaussian distribution. So if you had Gaussian distribution, then you can just work that way as I was suggested before. That if v cubed goes as just proportional to a, then v to the n would go to a to the power of n over 3. So if we had Gaussian statistics, if we had Gaussian statistics, what does it mean? The Gaussian statistics. It means we call a function. We call function to be a Gaussian function if the increments of the function have Gaussian statistics. Let me write it. For a function, we say that a function f is a Gaussian function if increments of f, let's see, fx minus f naught, f at 0, a random function, in a certain sense random. So it's a function for which we can have different realizations. If that function increment has, if fx minus f naught has obeys Gaussian statistics. So something like we take here a probability density function. Probability density function here is probability and probability density, and here is delta f, which is defined as fx minus fx naught, f naught. And okay, here is 0, 0. And then if it has a Gaussian distribution, something like that. Then I say that it is Gaussian. But if we have intermittency, then we have a significant departure from Gaussianity. So if we had here a power law tail, something like maybe going like that. So this red goes down as proportional to e to the power of minus certain factor a multiplied by x squared. Then it goes down like a Gaussian function. exponent of -x squared. But even if it goes like e to the power of maybe -ax, which is also much slower than the Gaussian, or maybe even as a power law as x to the power of certain -n, certain power of x, then in both cases we have significant non-Gaussianity. This is power law tail. And this guy here over here is exponential tail. Because exponential may seem to go fast down, but it is still slower than Gaussian. And both these make it intermittent. If you have non-Gaussian statistics, then if essential non-Gaussianity, then you say that you have intermittency. And if you have intermittency, then you have, going back to the previous slides, and we have the non-trivial structure function scaling exponents. So as long as you have Gaussianity, then structure function scaling exponent is linear function of n. But if you have a significant intermittency, then this is no longer the case, and the exponent xi can be a significantly nonlinear function of n. And now I think it's also somewhere during the lectures what was discussed that intermittency is definitely present in the case of velocity field, in the case of turbulence. So if we make something like psi as a function of n, psi, and here is index n, and here is like n goes 1 and 2 and 3, and then we have 1. And we know that the graph needs to go through point n is 3, then xi is 1, because v cubed is proportional to just scale a, but we don't know the rest. So if we had no intermittency, it would be a straight line. No intermittency. But the real life is different. The real life, it goes maybe something like that. It's curving slightly. But it is still the departure from, in this case, is not very strong. But it is, things are quite different if we speak about the passive scalar. So we can do the same thing with passive scalar. And then we have something like, if you consider temperature differences. Temperature differences in turbulent flow. Then we have total scalar or total temperature is conserved. Then we have temperature associated with scale A. Then temperature fluctuations. Again, similarly transferred to smaller scale. So we learned that there is a stretching and folding actions and gradients of temperature or tracer density become characteristic scale becomes smaller. The gradients are magnified, and so there is also a certain spectral cascade towards smaller scales for temperature fluctuations. The same way as before, we separate here temperature fluctuations, coarse graining of temperature. We can say that during certain characteristic time tau, energy is transferred from scale A to A over 2, and so the spectral cascade then becomes temperature associated with scale A divided by characteristic time associated with scale A. But that characteristic time comes from the Kolmogorov turbulence, so this must be constant. But from Kolmogorov turbulence, we learned that tau sub A, tau is estimated as like hydrodynamic rotation time of a vortex, A divided by V, and V is proportional to A to the power of 1/3, so that this whole thing becomes now A divided by A over 1/3 is A to the power of 2/3. And so we obtain from here, combining those two results, we obtain that TA squared should go as tau A, which is A to the power of 2/3. So we take a structure function T at X minus T at X plus A, and take here now square and average, then that should go as A to the power of 2/3. So we can, but then again, we can do the same thing that consider structure function, which now is T at X minus T at X plus A to the power of N. And then this goes as A to the power of structure function N. In the same way as before, we can say that if we had no intermittency, then if we take here psi, if we take psi and here N, and take here 1, 2, N equals 2, and then psi should take value 2 over 3, 2 over 3. Then the curve should go through this point. That would be linear. That would be ideally in no intermittency case. But here, the real life is very different. It goes something like that. It almost like becomes saturated. And well, I think maybe we need to stop here with the increasing intermittency. I guess this might be all a topic for next lecture, probably, or something like that. Maybe just don't go too far with it. Now, how are you with those structure function scaling exponents and intermittency?
Well, for me, it's a bit, I don't know, kind of confusing. I guess I don't understand like the point of it, maybe. Not sure.
For me, it is confusing.
Okay, but then go ahead and ask, and let us try to make it less confusing. So where it starts to get confusing, at which point?
So I understood what were like the conditions for like intermittency, but like after that, I kind of lost track.
Okay, all right. So how is that? So you understand that power law tails, but not why we have that structure function scaling exponent going nonlinear. Is that right?
I guess so, yeah.
Okay. So let us see. We can do it also mathematically, kind of. Suppose we have now probability distribution function P of delta F, okay? Which is a delta F is. It might be velocity increment, it might be temperature increment, doesn't matter. And now this is certain, that's a certain function of delta F. It might be exponent minus IAX minus delta F squared, but it can be something else. And now a power law, delta F to the power of minus n, for instance, something like that with certain n. And now we want to calculate how behaves delta F. But delta F itself is a function of A. So we can consider temperature increments at scale A, okay, small scale A and big A. And now how can that intermittency starting playing a role in structure function scaling exponent? So in order to find structure function scaling exponent, what we need to calculate is nth power of delta F. Delta F to the power of n and average. Now what this is? This is integral a delta F to the power of n, a P a delta F, and D delta F. That's it. Okay. And now if we have P of delta F, if this is Gaussian, and then this is more, what is Gaussian property is that it is non-zero within certain characteristic scales and then goes very fast down. So we have only a characteristic range of a certain of those scale, how we denote it now, certain width W. So this is delta F. So for if as long as delta F is smaller than characteristics that width, its P is on the order of unity. But if delta F is bigger than W, then P is approximately 0 because it goes down very fast. So whichever power you take, you can say that, okay, this integral is estimated as a W to the power of n. The characteristic value after which the BDF goes to 0. But on the other hand, if it goes down slower than Gaussian function, then what might happen? So look here, what you need to calculate. You need to calculate delta F to the power of n multiplied by P of delta F. So suppose now we have slow P of delta F. And then we multiply by delta F to the power of n. And now let me draw it there maybe. So P to the power P to the multiplied by delta F. Let it go something like that. So this is P times delta F. Now we make P multiplied P square P multiplied by delta F square. This goes something like that. And then we can take P delta F cube, maybe 4 or 5, something like, let's take something big. So this is P delta F to, let us say, maybe 5. So you can see that the bigger delta F you take, the farther away you move. So maximum here was here. Maximum here is rightwards. Maximum here is even more rightwards. And the more you increase the exponents, the more you move rightwards. And so now that P to the power of delta F5 is already, you cannot say that contributions are now made with the same type of characteristic width here. It says this is W width. But now contributions are made here already at several W, maybe 2 or 3 Ws. And and that's why you are moving. You cannot no longer say that this delta F to the power of n can be estimated as omega to the power of n. So what you have here playing role are extreme events certain so delta f to the power 5 average is dominated not by the main events, but those events which are very seldom happen, but still because you calculate now a fifth power, they still play a role. So in the case of intermittency, extreme and very rare and very extreme events starts playing role, and like define actually how these high powers behave, how averages of high powers behave. That's why if you don't have a Gaussian law, a Gaussian distribution, then these there will be nonlinear behavior in the structure function scaling exponents, because depending on the which contributions are made in the structure functions depend on which power you take. The higher power you take, the different type of extreme events you measure. If you take structure function exponent 2, you measure moderately big events, but if you take power structure function exponent 10, then you measure mostly the very most extreme events. And now they are quite different. Moderately big events and very extreme events, they are quite different. And now it depends already specifically what shape that P of delta F is. Now, was that helpful?
Yeah, that was better, but what is the exact definition of P? Is it like probability or what?
Probability density functions. This you should have had during your statistics courses. So that probability is obtained as P multiplied by dx. So if you have random variable x, the probability of x taking value from x to x plus delta x, so P times dx, probability of having x in the range from x to x plus dx. This is the what defines probability density function P is PDF. PDF, probability density function. Okay. And yeah, intermittency in the world around us is actually a very significant and important thing. And you can find examples of intermittency quite often. Like, well, I think a few years ago during this course, I gave example of intermittency, which is quite nicely described in a book of which I myself read when I was quite young, going in school, written by a Russian mathematician, I think he was, Yakov Perelman. And the book called Mathematics Can Be Entertaining. And that he describes situation when one mathematician is arguing with other guys and making a bid that are arguing what how likely it is to have 100 subsequent persons you meet on street. Then you go out. What is the probability that that 100 first persons what you meet are all male? Probability first persons are male. Simple-mindedly, you can estimate it like that. Probability that first person is male, saying that men and women are equally distributed, would be 1/2. And so you would estimate it 1 divided by 2 to the power 100. Okay. Now, is this number big or small? We know that 2 to the power of 3, 2 to the power of 10 is around 1,000. 1,024 more exactly. 1,000. So that 2 to the power of 100, 2 to the power of 100 is around 1,000, which is 10 to the power of 3 to the power of 10. Is 2 to the power of 10 to the power of 30. Now, is this big or small? Of course, it's very big, and probability is definitely very small. So how long would you need to wait to have this happen? So let us say that you meet 1 person per 1 second. So how long you would need to have this happening is something like 10 to 30 seconds. How many years is it? It's quite many. Second. Now, 1 year is how many seconds? We have 24 hours, 3,600 seconds, and we have 365 days. Now, how much is it? Just approximately. How many zeros we have here? We have 3 zeros. Here is 1 more, 4. Here is 5, and then 2 times 3 times 3 gives us another 1. It's something like 2 times 10 to the power of 6. Is it 1, 3, 1, and to add 1 more? It is 2 to 10 to the power 6. So 10 to 30 seconds is well at least something like 10 to 24 years. And now how old is universe? Universe is universe is around 10 to 10 billion years. Yeah, 10 to 10 years. And how it compares, so it's much longer. You need to have like a trillion universes to have this happening. And now the story by Jakob Perelman goes that okay, mathematician makes a beat that makes very big stakes, like putting out that first 100 persons are not, it will not be happening. That you have at least some women inside of them, and then they go out to check, and then army drill is being made, and all of them are male, of course, and all this breaks down. So what does this show? It shows that actually human society is very intermittent. So calculations which make like an assumption of causality fail because you have such kind of otherwise extremely low probability events still taking place. So this is one example of how, in which way human society is intermittent. I don't know how useful it was in terms of turbulence, but just in generally speaking about this role of intermittency in everywhere in nature, I think this is quite a nice example. All right, coming back to turbulence, anything else you want to ask here? And we're speaking about lecture number 14. So is everything now for lecture 14 more or less clear?
Well, clear is a strong word, I would say.
Okay, the main messages, let us say. And should I list here the main messages?
Yeah, I think it would be a good idea.
Okay. Okay, so first we have Kolmogorov turbulence, which means that we have direct cascade 3D and 3D direct cascade. Energy goes to smaller scales, vortices. V is characteristic speed of vortices is proportional to the scale to the power of 1/3. And P of K, K to -5 5/3. Then okay, what also important concept what you need to know is okay, concepts of Kolmogorov microscales. Kolmogorov microscales. So why is this important? This is just to understand when you have Kolmogorov turbulence and when you need to consider the power laws. And just knowing what is my Kolmogorov microscale, like let's say atmospheric, typical atmospheric motion, something like around millimeters. So everything which is above millimeters, we have Kolmogorov scaling, and below you have small behavior. And then concepts of Kolmogorov microscales. You have different microscales. You have for length, you have for time, but then there is also concept of inertial range. I am not repeating it here because we had that written down before. Inertial range. So these are important concepts just to more or less have an idea what they are, what I'm speaking about. Then we have inverse entropy cascade in 2D, the inverse energy cascade in 2D, which means that the energy goes to larger scales. Instead, and think about cyclones and anticyclones. Which are big. And then we have intermittency. intermittency. What does it mean? It means that extreme events are important. Extreme events, even so, with small probability, are very important. If you go to insurance business, for instance, then you definitely need to know that extreme events are important. So what does insurance company do? Smaller insurance companies make some further insurances to bigger companies, that if for some unfortunate events they run out of their funds because of extreme events, then the bigger companies which have more money can help them. So just to try to insure against some very extreme events. And this is what you always need to keep in mind, that all nature is actually very intermittent, and always very big events can happen. Like you have, you can think of also about extinction of dinosaurs. Dinosaurs due to very extreme event of some huge comets falling due to extreme events. And so on. So I'm sure you can think about how extreme events have played a role in nature and in history. And then, it would be also nice to, if you remember what are, try to remember what are the structure functions. What are the structure functions? And they are which are related. Which are tools to describe intermittency. So if we did not have intermittency, there would be no need to have structure functions. So structure functions are one way of describing or characterizing, to characterize intermittency. And that's it probably. And yeah, I think there was also, you asked about the bottleneck. So this was also, we still have some time. We can briefly go through bottleneck as well. And let us put it also here. 6 was about bottleneck. Rain initiation in warm clouds. The bottleneck. Now, since you asked about the bottleneck, so what is it about? It is about why rain, if you have a cloud, so how it happens that rain falls out fairly fast. So bottleneck. Rain initiation in warm clouds. So what is the problem? You have, if you have surface of Earth, and now you have here down here we have humid here and heating. If it's heating, so what happens is that air masses move up. Once they move up, they move up adiabatically. So in that case, you have what you call adiabatically, you have adiabatic atmosphere. So say cool down. So because they cool down, what happens is that relative humidity goes up, because the saturation pressure will go down. Saturation pressure of vapors, water vapors. Of water vapors goes down. Now, if it goes down, so relative humidity goes up. Oops. Because this is a ratio of the water vapors divided by the saturation pressure. This goes up, and this goes very fast down because this exponentially depends on saturation pressure. It depends exponentially on temperature. That's this is a very fast process. It goes saturation pressure goes very fast down. So this dominates in the expression for relative humidity. Relative humidity goes up, and then that's why you have cloud form. So once relative humidity reaches 100%, then this is a lower boundary of cloud. So that's why you have also usually a lower boundary of cloud is flat. Upper boundary can be non-flat because it depends how far the vortex is carried. This is like a prime example of Kolmogorov turbulence, the upper boundary of clouds. But lower boundary is flat because this is a height at which humidity reaches 100%. And now you have cloud here, and you have what it is actually. You have a lot of very small droplets. So actually, you need to have something like a certain oversaturation. R is around 101% or so. Then you have small droplets, mist appearing. So why do you need a little more than 100%? Is because you need to have nucleation centers. Water can condense only on a water surface, but if you are very clean here, there is no water surface, or any surface where the water could start condensing. So you need to have that nucleation centers. Which are usually very small in size, and that's why you just the capillary pressure increases a little bit. So you need to have a higher, effectively, you need a higher relative humidity to form very small droplets. And so now you have nucleation center, and around it you have a water. And now if this droplet goes up, then it grows bigger, because here, if here R was 101%, and maybe here is 102%. And now all the excess water goes into here, and so it grows. The higher it goes, the more water it takes. But now the thing is that all the droplets have the same size. The problem. All droplets have the same size because how big they are depends how high they are. If they go up, the radius increases, but if they go down, it again decreases again back. And so they lose the excess water then. And they, as they move, the size, they either obtain size or lose it. And now, how you can start water going out, rain falling? You need to have big droplets. But this way you won't have very big droplets. So, because even if you move to the very high of the cloud, you still have so small droplets which are just being carried with the air because of a viscous drag. A viscous drag still keeps viscous drag. Viscous drag keeps the droplets hovering. You know that if you have mist, droplets are not falling down because they are very small. Now, in order to have droplets falling down, you need them to collide. So, because there are plenty of them, even if they rise very up, they will not be big enough to fall down. In order to have them big enough, you need to have them colliding. In order to fall down, the droplets need to collide. So if two droplets merge, one bigger droplet is formed. But now they move together with the air and they cannot collide because they are just move as the air moves. And now, if you make simple estimate, if you make estimates, you will learn that it would take something like 10 hours. For the droplet to fall down. For the droplets to grow big enough, to fall down. But in reality, it falls down around half an hour or hour. So much faster by order of magnitude. And that's what is called bottleneck problem. It's a bottleneck problem. This is about what is called bottleneck, that theory predicts, if you make simple estimates, how long it would take for the droplets to grow and start colliding because of gravity. it would take 10 hours, but in reality it happens in 1.5 or 1 hour. And now how it can be explained that actually it happens, it's also actually in terms of intermittency, that we say that also the intermittency of Kolmogorov turbulence, as we discussed before, is not very big. There is certain intermittency, but not very big. Here, the departure from a linear law of the structure function is not very big. But even though it is not very big, intermittency is just strong enough to make it so that below the Kolmogorov microscale, there are still smaller vortices, which make some of the droplets start colliding and then start initiating rain. In order for rain to start, you need to have some droplets which are bigger than the others. So, intermittency can explain it. Okay, I think we are our lecture time is more or less ending, or it already ended. So I think we can put it stop here. So just for bottleneck, if you know as much as I told right now here, then I think it's good enough more or less. That there is bottleneck problem. Its explanation is in terms of the intermittency and what they also call a sling effect, but this is probably we don't discuss it right now. I think we have a certain degree in the lecture recording about sling effect as well. Now, whoever asked about the bottleneck problem, Kaspar probably.
Again, not Kaspar, it was me.
Okay, yeah, all right. Yeah, so how is it?
Yeah,
No,
it
just
was
very
good.
roughly, just so you know about the concept and what is it about.
No, when you explained like the intermittency example with the two mathematicians and combined this, it's actually quite good.
All right, then we are done for today. And one more lecture to go. So. Anything you want to ask still, or can we finish for today?
I think everything seems pretty much clear.
All right, then that's great to hear. And until next time.
Thank you. Bye.
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 Goodbye.
Bye.